It's a pleasure to be here in Scotland. So, as we very well know, in complex analysis, it's customary to consider the unit disk with the hyperbolic metric. In this case, automorphisms of the unit disk act as isometries, while the Schwarz lemma says that holomorphic mappings are contractions. After Mobius transformations, the simplest holomorphic submaps of the disk are finite Blaschke products. And here you could see two dynamical portraits of finite Blaschke products. So a finite Blaschke product is a holomorphic submap of the disk, which is asymptotically a hyperbolic isometry. So as you approach the unit circle, a finite Blaschke product becomes more and more like an isometry. It's well known that a finite Blaschke product can be represented in this form. And often this is used as the definition. However, I do not like to use this as the definition because it privileges the locations of the zeros of F. So F vanishes at the points AI. In this talk, you'll take a less traveled route and study finite Blaschke products from the perspective of their critical points. From this point of view, the fundamental theorem is due to Maurice-Hines, which says that any finite set of points is the critical set of some finite Blaschke product. And moreover, this finite Blaschke product is essentially unique. And when I say unique in this talk, I mean unique up to post-composition with a Mobius transformation. So from the chain rule, we have this. And this never vanishes. Therefore, M composed with F has a critical point if and only if F has a critical point. So while Hines' theorem is a statement in complex analysis, the proof involves nonlinear elliptic PDEs. More precisely, the proof involves the Liouville correspondence, which provides a bijection between homomorphic submaps of the disk and solutions of the Gauss curvature equation. In practice, it's somewhat difficult to find questions which are interesting in both settings. So to explain how the Liouville correspondence works, suppose F is a homomorphic submapping of the disk, then it defines a conformal pseudometric lambda F, obtained by putting back the hyperbolic metric under F. Now, lambda F is only a pseudometric. It could vanish at the critical points of F. Now, the hyperbolic metric has constant negative curvature -1. By Gauss theorem egregium, lambda F also has constant curvature -1. except at the critical points of F where it has measure-valued singularities. This fact can be expressed in terms of the function UF, which is log lambda F. And then this just says that the function UF satisfies the Gauss curvature equation with integral singularities. Remarkably, the converse also holds. Any solution of the Gauss curvature equation arises from a holomorphic function. And moreover, this Liouville map is unique up to postpropositions with Mobius transformations. So let me give a quick sketch of the proof of Heinz theorem. So the hard part is to show that there exists a finite Blaschke product with a given critical set. So we define UC to be the pointwise maximal solution of the Gauss curvature equation with the appropriate singularities. Namely, the solution which dominates all other solutions pointwise. Now, this may seem a little bit strange. For instance, if you take a look at the Laplace equation, it has no maximal solution. So to specify a particular solution of the Laplace equation, we could prescribe some boundary values. So if you let UN to be the solution of the Gauss curvature, of Laplace's equation with constant boundary values n, then UN is the constant function n. And as n tends to infinity, the functions blow up. However, in the Gauss curvature equation, we have this term, e to the 2u. And this nonlinearity makes the solution highly subharmonic. So when you do this procedure for the Gauss curvature equation, the solutions UN do not blow up. They actually converge to the maximal solution. Once you have found the maximal solution, we could use Liouville's theorem to produce a holomorphic submapping of the disk FC. And finally, one could use the maximality of the solution to show that FC is indeed a finite Blaschke product. So,
what does it exactly mean, maximal?
Pointwise maximal dominates every other solution pointwise. So give me any other solution, this solution is bigger.
Mm-hmm.
So the proof of 3 uses hyperbolic geometry. When I say hyperbolic geometry, I'll mean one particular fact from hyperbolic geometry. Suppose you have a curve gamma such that its hyperbolic geodesic curvature is bounded above by a constant less than 1. In this case, gamma is a quasi-geodesic. In particular, it lies within a bounded hyperbolic distance of a genuine geodesic. So I also want to mention the work of Daniela Kraus and Oliver Roth, who considered what happens when C is an infinite set of points. So there are two possibilities. So this is Daniela Kraus and Oliver Roth. So if there is a bounded holomorphic function, with critical set C, this procedure produces a particular Blaschke product with critical set C, called the maximal Blaschke product. While if there is no bounded holomorphic function, with critical set C, the Gauss curvature equation has no solutions, and this procedure produces nothing. Now we come to inner functions. So as Gwyneth mentioned, an inner function is a holomorphic self-mapping of the disk such that for almost every radial direction, the radial boundary value exists and is unimodular. Like Riemann surfaces, inner functions can be very, very complicated. So therefore, one often restricts to particular classes of inner functions. So finite Blaschke products correspond to compact Riemann surfaces. The main player of this talk would be inner functions of finite entropy. And they are precisely inner functions with derivative in Navalina class. So here I have written a formula. The integration takes place over the unit circle. But F is defined only on the unit disk. So for this formula to make sense, we require that F prime has boundary values almost everywhere. So finite entropy inner functions correspond to finite area Riemann surfaces. And finally, I want to mention the class of one component inner functions. And they are inner functions which Alex might like. So if mathematicians from operator theory haven't discovered one-component inner functions, most likely they would be named after Alex. So their inner functions, those sets of singular values, are compactly contained in the disk. And here I say they behave sort of like convex co-compact Riemann surfaces. So this is my page from the Sullivan dictionary.
So your finite entropy functions automatically one component inner functions?
No. So those classes have an intersection, but one does not contain the other.
If it is one component, can you somehow interpret the finite entropy condition in terms of
Yes.
okay.
Okay, so
So what does it mean, convex co-compact Riemann surface?
so that's a great question, and you should ask the experts. I just put something random here. Okay, so I'll draw a picture. So take the unit disk and consider the Fuchsian group generated by reflections in 3 geodesics. The fundamental domain is this region here. And it's not compact. However, if one takes the convex hull of the limit set and mods out by gamma, one actually gets a compact region. I hope this answers your question. But maybe I do know what this means. So since there are many experts in dynamical systems, I wanted to mention some results about the dynamics of inner functions. So we say that an inner function is centered if it has an attracting fixed point at the origin. If the Danjoy-Wolff fixed point of F lies inside the unit disk, we could normalize it so that it's centered. In this case, the big measure on the circle is invariant under F. In fact, it's also ergodic and mixing. These facts have been proved by a number of mathematicians, including Lohner, Pomerenke, and Shub-Sullivan, just to name a few. The proofs use harmonic extensions of characteristic functions. So the proofs are pretty elementary. Now I want to say a few words about the central limit theorem. Suppose h is a function on the unit circle, and we use the standard notation as an h to mean the sum of h along the forward orbit of x. one says that the central limit theorem holds for an observable h of mean 0 if S and h over root n converge to the Gaussian normal distribution. And with Mariusz-Urbanski, we show that if h has some smoothness, so if h lies in the Holder class or is a Sobolev multiplier, then the central limit theorem holds. I also want to mention that a different central limit theorem has been proved by Artur Nicolau and Odile Soler et Gilbert, which concerns Blaschke lacunary seal. So they only showed the CLT for one observable, but they allowed weights. So their work is somewhat orthogonal to ours. If one wants to go beyond the CLT, one should restrict to a subclass of inner functions. So here I want to mention a theorem of Marcos Kreiser. So recall that if f is a centric inner function, then f preserves Lebesgue measure. So one can inquire about its measure theoretic entropy. And Kreiser showed that the measure theoretic entropy is given by this integral expression, which is often called the Lyapunov exponent. For nice dynamical systems, so words like hyperbolic or axiom A, it's well known that the Hausdorff dimension of a measure equals to its entropy divided by its Lyapunov exponent. For a big measure on the circle, the dimension is 1. So one expects that entropy equals to the Lyapunov exponent. However, inner functions are anything but nice. So inner functions can be singular at every point on the unit circle. So the proof of Kreiser is actually quite sophisticated.
So probably for one component functions, it would be easier.
Yes, a lot easier. So I want to mention some results on orbit counting with Mariusz-Urbanski. Sorry, I'm not very good with blackboards. So let Z be a point in the unit disk, which is not the origin. And we look at two repeated preimages of Z. That is points W, which map to Z in some number of steps. Given a number R, we can count the number of repeated preimages which lie inside the ball of hyperbolic radius R. The following theorem says that NZR goes exponentially quickly up to a Cesaro average. The standard way for proving orbit counting theorems is via thermodynamic formalism, dynamical zeta functions, and Tauberian theorems. However, with this approach, one needs to ask some stronger integrability condition on the inner function. I don't know how to get rid of this epsilon using this approach. So for me, however, this theorem makes sense precisely when F has finite entropy. So essentially, we prove the sharp result. So if you have heard my talk in Poland, this theorem is new. It says that under slightly stronger assumptions, so assuming the one component condition, we have the full orbit counting theorem without the Cesaro average. Use the ergodicity and mixing of the geodesic flow on the Riemann surface lamination associated to F. So a Riemann surface lamination is an object which is locally a disk cross a Cantor set. So it's quite different than the notion of a lamination on a Riemann surface. So Riemann surface laminations were introduced by Dennis Sullivan in connection to renormalization. The geodesic flow or a Pari-Blaschke product has been introduced by Kurt McMullen. And most of the work proving this theorem is about defining the geodesic flow in the context of one component inner functions. Sorry, in the context of finite entropy inner functions. So basically, we show that along almost every backward orbit, the dynamics is asymptotically linear.
What is the lamination for your inner
I'm not going to define this.
Is it some backward orbit kind of?
Yes.
Okay, natural extension.
Yes.
Is there any chance to get the error term?
There is no chance to get error terms.
That's because of your proof or no chance in
Because of the proof.
But for finite products,
Yes. So for finite products, some works by Dolgopian. I should say that this approach is very general. For instance, it's also applicable to rational functions. Suppose R is a rational function satisfying three conditions. First, it has a conformal measure. Of dimension alpha. So I should say that the measure should live on the Julian set. Second, it has an absolutely continuous invariant measure. And the third condition is that the radon-nicotine derivative should be bounded below. So under those three conditions, the orbit counting theorem holds. So the three conditions are satisfied for topological colored Ekman maps, but Mariusz told me that the class of rational functions is actually a lot larger. So actually for rational functions, the strategy is a lot easier because one doesn't have to work with a Riemann surface lamination or use some kind of hyperbolic filling like the barycentric extension to hyperbolic 3 space. One can make the argument on the suspension of a natural extension.
You don't use the Lubitsch-Minsky elimination or anything.
I tried to read their paper for years, and I think I succeeded somewhat, but this is just easier.
When you say the orbit counting, do you mean counting pre-image points?
Counting pre-images, not periodic orbits. You can't actually count periodic orbits for inner functions.
No, but for TCE maps.
So for TCE maps, only pre-images.
They were disjoint.
So yeah, so I only started thinking about the stuff quite recently.
Yes.
Okay, so that's all I'll say about dynamical systems. Okay, so back to analysis. So here's a question. Can one parameterize inner functions by their critical points? Unfortunately, the answer is no. So here on the slide on the top, we have the universal covering map of the punctured disk. And being a covering map, it has no critical points. Well, the identity mapping also has no critical points. So one needs to record more information. So what I want to say is that the universal covering map of the punctured disk, hello, here, has a boundary critical point at -1. So take the slit from 0 to 1, drawn in red, and its pre-image under F is a countable union of curves. And the map F maps every complementary component to the complement of the slit. And what you can do is you can take this map F and approximate it by finite Blaschke products. Fn, which has a critical point C of high multiplicity. So somehow, since in this picture you have critical points, and those pictures converge to this picture, it's natural to say that -1 is a boundary critical point of the inner function f. To make this precise, we need some terminology. So any inner function can be written as a product of a Blaschke product and a singular inner function. The Blaschke product, p of z, records the zeros of the inner function, while the singular inner function is an exponential. It has no zeros. Exponentials do not have zeros. The way you can think about singular inner functions, you can think of them as degenerate Blaschke products, where the zeros have been pushed out to the boundary in a controlled way. And mu here is the limiting distribution. So let's go back to inner functions of finite entropy. And we are going to endow this class with a stable topology, where a sequence of finite Blaschke products Fn converges to F if the entropies converge. The word stable comes from Nevelina's table. So this condition is equivalent to the inner parts of Fn prime converging to the inner part of F prime and the outer part of Fn prime converging to the outer part of F prime. In other words, the Nevelina splitting is stable in the limit. So it's well known that if you have such an inner function of finite entropy, it has a Boston Symphony Orchestra into a Blaschke product, a singular inner factor, and an outer factor. So we define the critical structure of, So in this decomposition, the Blaschke factor records the critical set of F, while the singular factor records the boundary critical structure. So when I say the critical structure of an inner function, I mean the B times the S. And it's because I record this S, I can distinguish the universal covering map from the identity function. And so the following theorem answers a question due to Konstantin Diakonov. To what extent is an inner function determined by its critical structure? And what are the possible critical structures of inner functions? So the theorem says that an inner function is uniquely determined by its critical structure up to post-composition with a Mobius transformation. And the possible critical structures, the Blaschke factor can be anything, but the measure mu should be sufficiently concentrated. Namely, it should live on a countable union of Berlin-Carlson sets. So what this theorem is saying is that in order to prescribe an inner function of finite entropy, you need to give me a Blaschke sequence and a measure on the circle satisfying this condition. So given this data, there is a unique inner function with that critical structure. So it's like a very nice parameterization of the space. So Daniela Kraus worked out the case when the critical structure is a Blaschke product. And my role was to work out the singular factors. I should say that this condition, countable union of Berlin-Carlson sets, appeared in two independent works by Boris Kornblum, who we met during IMO's talk. And James Roberts. So I spent a lot of time studying Kornblum's work because he's the more famous mathematician of the two. But one day on August 8th in the summer, I looked at the paper of James Roberts and I immediately recognized that it was genius. Basically, he explains how to think of such measures. Okay, so here's the technical condition. A Berlin-Carlson set is a subset of the circle which satisfies three conditions. First, it is closed, it should have measure 0, and the sum over complementary arcs should be finite. Okay, so now we come to the main object of our talk. Given a finite Blaschke product, we can define a critical point measure, mu f, and a critical value measure, mu f. As the name suggests, the critical point measure, mu f, is supported on the set of critical points of f, while the critical value measure is supported on the set of critical values. The two measures have the same mass, but different distributions. The question is, can we extend these definitions to inner functions in a meaningful way? For instance, so that they are continuous in the stable topology. But first, let's return to this example. So what we can do is we can approximate f by a sequence of finite Blaschke products. Now, each Fn only has one critical point, but it has high multiplicity. So the critical point measure of Fn is the delta mass at C, while the critical value measure is the delta mass at the origin. So what we do is we take the limit as n tends to infinity, and it's natural to define the critical point measure of f as the delta mass at -1, and the critical value measure as the delta mass at the origin. So we come to the first main theorem of this talk. Suppose f is an inner function of entropy, and we have a stable approximation by finite Blaschke products. In this case, the critical value measures, nu of n, converge in the weak star topology to some measure nu f. This theorem has two surprises. The first surprise is that the measure nu f does not depend on the choice of approximating sequence. The reason this is so surprising is because in complex analysis, we use the topology of uniform convergence on compact sets. However, in those examples, the critical points escape compact sets. So why should we be able to say something about the locations of their images? So,
Stable approximation.
well, yeah, so in a stable approximation, we require this. And it turns out that this topology is actually quite a bit stronger than uniform approximation on compact sets. So maybe I could give an example. So if you take a closure of finite Blaschke products with the topology of uniform convergence on compact sets, then a theorem of Karafi-Lowry says that we get the unit ball of bounded holomorphic functions. So by contrast, if we restrict the entropy be bounded by a certain number, then this set is compact. In particular, the limit of inner functions is always an inner function. So this topology is actually quite strong. The second surprise is that the measure nu f is supported on the open unidisk. Of course, the measures nu fn, given by this formula, are supported on the open unidisk. But when one takes weak star limits, in principle, one could get a measure supported on the closed unidisk. So what 2 says is that while the critical points can go off to the boundary, the critical values cannot. They're kind of stuck inside the disk. Our main tool is the notion of a component of an inner function. This tool was first used by Christian Pomerenke in his seminal paper on Green's functions of Fuchsian groups. Suppose V is some Jordan domain in the disk, and U is a connected component of its pre-image under an inner function f. One can show that U is always a Jordan domain. In particular, U is simply connected. So we could compose F with Riemann maps. And this gives us a component function, Fu. One can then show that Fu is always an inner function. Furthermore, if F has finite entropy, then the component inner function Fu has finite entropy. The second theorem tells you what Fu is. So to describe an inner function of finite entropy, you need to describe its critical points and its boundary critical structure. The critical points are easy to describe. The critical points of Fu are the preimages of the critical points of F which lie inside U. The boundary critical structure is more complicated and features an angular derivative. So I want to say a few words about angular derivatives. So let's say you have a conformal map onto a Jordan domain. One says that phi has an angular derivative if the limit as r tends to 1 of p prime r zeta exists and is finite. The Rotin-Warshawski theorem gives an if and only if condition for phi to have a non-zero angular derivative in terms of a modulus condition quite similar to the ones we saw in Milcana's talk. In our case, we will discuss conformal maps to regions omega contained in the unit disk. And in this case, the Rotin-Warshawski theorem takes a simpler form. Namely, it says that phi has a non-zero angular derivative at a point zeta, if and only if omega is sufficiently thick at phi of zeta. So, for instance, it's necessary that omega contains a Stolz angle of arbitrary opening at phi of zeta, but this is not sufficient. Okay, and one more definition. The notion of a thick limit. We say that a function f has a thick limit L at a boundary point zeta if for every epsilon, some connected component of the preimage of the ball centered at L of radius epsilon is thick at zeta. So it seems like a reasonable definition. And I was very happy when we have invented this, but it turns out to be equivalent to F having a minimal fine limit from potential theory. Okay. And finally, I can state the third main theorem of this talk. Suppose F is an inner function of finite entropy and assume its critical structure is B times S mu. In this case, for mu almost every point zeta, F has a thick limit which lies in the open unit disk. And this theorem may seem kind of strange because usually inner functions have radial limits on the circle, but they have radial limits on the circle with respect to a big measure. And here we are discussing the behavior of F with respect to a singular measure. So we didn't seek out to prove theorem C. The reason that we proved theorem C, the reason we came to this notion of thick limits, is because it was absolutely necessary to prove theorem 1. So we were forced into this. We did not guess this. To give an example of this theorem, suppose mu is a singular measure on the unit circle, which lives on a Berding-Carlson set E. In this case, then for mu almost every zeta, this integral is finite. This integral may look very strange because here you take the mass of a ball to a negative power. But in fact, it's very natural from the perspective of building Carlson sets. So I was going to say a few words about how this is proved, but I think I'll just stop here and wish Alex a very happy birthday.
Very much. Are there any questions or comments?